An equation can be derived to relate a force to the change in momentum it causes. We'll be doing some algebra that's trickier than what we usually see on this course, but you'll need to be able to do this derivation yourself or explain it in words, so make sure you can follow along and understand how this works. Before we get started though, we should first understand how to calculate a change in momentum. Remember that the momentum of an object is given by momentum equals mass times by velocity, or algebraically, P equals m times v. Suppose we had an object at two different times. At GCSE, you won't encounter problems when a single object's mass changes, so we can label the mass at both of these times as m. Then we'll call the starting velocity u and the final velocity v. The change in momentum is the difference between the starting and final momenta. We can write this as p end minus p start. Since momentum is mass times velocity, we can rewrite this as mv minus mu. Now, since both of these terms involve us multiplying something by m, we can factorise this out to get m bracket v minus u bracket. Now we have the difference between the end and the start momenta on the left, and the difference between the end and start velocities on the right. We can then simplify this equation by writing it as delta p equals m delta v, where this triangle is the Greek letter delta. In algebra, it usually means change or difference. So in words, this is the change in momentum is equal to the mass multiplied by the change in velocity. Now to figure out how this equation can be related to force. First, we'll start by reminding ourselves of the equation for Newton's second law. That is, force equals mass times by acceleration. Or algebraically, this is F equals ma. Now we should remind ourselves of the definition of acceleration. It's the rate of change of velocity, or how much velocity will change as time changes. We can write this algebraically as A equals delta V over delta T, where we're using this delta symbol again. Now we're going to substitute this fraction for A in our force equation. This gives us F equals m times delta V over delta T. Remember that the substitution works because delta V over delta T will always be equal to A in our original equation. Now let's bring m into the fraction by putting it onto the numerator. We do this because multiplying the fraction by m is the same as multiplying the fraction by m over 1. So we get m delta v over delta t. Now this m delta v term should look familiar. Remember, we just found out that delta p, the change in momentum of an object, is equal to m delta v. So we can do another substitution, this time substituting m delta v with delta p. This fraction will then become delta p over delta t, which means it is equal to f. So in full, we have that f equals delta p over delta t. In words, this equation will be the force equals the change in momentum divided by the time taken, or the time the force is applied for. In other words, the resultant force on an object determines the rate of change of its momentum. You might see some textbooks refer to this as the more accurate equation for Newton's second law, but you don't need to worry about why that is at GCSE. As a reminder, you should be able to explain algebraically or qualitatively how we find this equation from F equals ma and the definition for momentum. Let's check what units we should be using for this equation. Momentum is measured in kilogram meters per second, and time is measured in seconds. Then force is measured in newtons. Looking at this equation, we can show that newtons are equivalent to kilogram meters per second, or per second squared. This is the same conclusion we'd reach using the equation F equals ma. Now let's see how to apply this equation to an example. A parachutist deploys a parachute in order to reduce their downward momentum from 4,000 kilogram meters per second to 600 kilogram meters per second in 1.2 seconds. calculate the average resultant upward force needed for this change in momentum. Give your answer to two significant figures. So here the drag wouldn't be constant, which is why we're asked to find an average force. We can do this just like finding an average acceleration by using the overall change in momentum. So for step 1, write down the key values and check the units. Some exam questions will give you the change in momentum directly, but here we need to find it ourselves. So to do this, we'll use the starting momentum, which is equal to 4,000 kilogram meters per second, and then the ending momentum, which is 600 kilogram meters per second. Then once we find this change, we'll use the time taken, which is equal to 1.2 seconds, to calculate the force. All of our units are as expected, so let's move on to the next step. Then for step 2, calculate the change in momentum. As we've seen, the change in momentum is found by subtracting the starting momentum from the final momentum. This is 600 minus 4,000 kilogram meters per second, which equals minus 3,400 kilogram meters per second. Notice we got a negative value here. This is because the resultant force would be directed opposite to the parachutist's motion, so this force is causing the momentum to decrease. Since the question specifies the direction of the force, we can just stick with positive values from here to make things easier. In step 3, calculate the average resultant upward force needed. We'll do this using our new equation, force equals the change in momentum divided by the time taken. Now we just found the change in momentum is 3,400 kilogram meters per second, and we're told that the time taken is 1.2 seconds. So the force is 3,400 divided by 1.2, which is equal to 2,833.33 newtons. But looking back at the question, there's one more step we need to do before we get our final answer. Finally, in step 4, round the answer to 2SF, which stands for two significant figures. To do this, we count the first two non-zero digits in our answer. 1, 2. Then we check the third digit, which is 3. Since this is less than 5, we round down the remaining digits to 0, giving us a rounded answer of 2,800 newtons.
Thanks for watching. If you want to take your GCSE revision to the next level, head over to launchpadlearning.com and check out our smart learning platform that's been designed to get you top results in your exams. We cover your whole specification and make revision fun with interactive quizzes, easy-to-follow videos, and more. You'll be kept motivated by your own AI tutor who's here to support you every step of the way. To check it out for yourself, click here. Or click here to keep watching a selection of the videos from our full GCSE Physics course. See you there!